As an academic, this is a pretty big house for me, so thank you all for coming out to Strange Loop and Papers We Love, and specifically my talk. So, like my beautiful introduction said, I'm here to talk today about programming languages and generally programming distributed systems. Oh, I'm going to torment the guy on the camera by just pacing back and forth. I'm so sorry. Well, let me just start by saying that programming distributed systems is hard. I mean, the modern world has seen an explosion of distributed systems of every kind. Simple applications like office software that used to run on a single thread in a single computer have become concurrent or replicated or even geo-distributed. I mean, I can't even edit my PowerPoint slides without logging into at least one cloud service, which it turns out requires another cloud service to sign into, which was down this morning. So these are backup slides. And much as my experience demonstrates, our ability to program these systems has not kept up. The results are predictable, an endless parade of bugs and security vulnerabilities as programmers grapple with every new leak in what were once reliable abstractions. We've built a cloud, and it works. And when it works, I can get my slides from Berkeley to St. Louis via Princeton, and it doesn't even blink. But we still don't really know how to program it. We still don't really have the programming language for the cloud. And in my work, I try to close that gap a little bit. This is Papers We Love, so I'm going to take you on a whirlwind tour of a bunch of papers I've written generally in this space, solving problems like destructive data races, dealing with coordination overhead across various distributed components. Oh, you guys are making me louder, all right. And handling consistency errors that can result. But before I can talk about any of these cool solutions, I'm going to need to tell you about my problems. What do I mean by a data race? What kind of coordination overhead am I worried about? And generally, what are consistency errors? All right, let's start simple with a data race. So a data race is something that is older than me, and it can happen whenever two or more threads simultaneously attempt to access memory, and at least one of those threads is writing. A classic example of a data race would be a split increment. Let's imagine that two different threads are both simultaneously trying to run instances of the program increment value at hexagon. And what'll happen is one of those threads will read, say, 5 from the hexagon, we'll increment it, write it back to our hexagon, and at the same time, just before that write happens, another thread will come, and it'll read 5 from that hexagon. And then it'll do the increment, and we'll write 6. Ultimately, we wound up losing one of our increments. Now, maybe there's some programmers out there that really like this behavior, but I claim this is normally a bug. And would in fact be an example of a destructive data race, which is just a data race that causes a program error. And it's a data race we've dealt with for years. We've got mutual exclusion locks in C. The keynote this morning referenced it as the one continuous language. And in the distributed context, we've got transactions. Transactions give us an abstraction of atomicity. It allows us to group our code into little blocks that all appear to happen at one instant. This will allow us to make sure either the entire orange or the entire gray thread will run at once. It's also kind of expensive. It turns out to be especially expensive if you're trying to deal with micro or nanosecond scale in single computers. Software transactional memory is any day now, but it has been for about 25 years. Let's put a pin in that, we'll get back to it later. But for now, we've defined a data race. Now let's talk about what my sources of coordination overhead and consistency errors might be. And in particular, we're talking about consistency as it applies to distributed systems. So if you used to work in memory, this is the analog of memory consistency in distributed systems. I'm also going to use it basically interchangeable with like database isolation levels. It's any set of rules that tells you what'll happen when you perform operations. Basically, a distributed consistency model says, if I'm going to perform a write at some replica of a replicated system, and I perform a read at some other replicas, what guarantees do I have about the relationship between that write and those reads? Am I going to read what I wrote? Am I going to read something newer, something older? Consistency models tell me. Now, the strongest consistency model that's in common use today is something called linearizability. Linearizability gives you the guarantee that if you perform a write at any replica, then you wait an infinitesimal amount of time and perform a read at any other replica, the effects of your write will have definitely propagated to all replicas before your read is allowed to execute. It's a very strong abstraction. It lets you completely ignore replication, but it's also pretty famously hard to implement efficiently. It works really well for smaller scales, like single data centers or single incredibly well-named Greek islands. Well, that tends to be our source of coordination overhead. And to handle that coordination overhead, the distributed systems community has invented a series of consistency errors. See, when you take a linearizable system and you scale it up to truly global scale, you have to contend with some unfortunate physical realities. The speed of light, as it turns out, is remarkably slow. It's only about, yeah, seriously, it's like 4 inches per clock cycle. And that was like 2 years ago. It's probably slower now. There's a lot of inches from London to Australia. I don't know what to tell you. At this scale, we've literally outgrown legacy consensus protocols that give us linearizability, like Paxos. We've also literally outgrown the island of Paxos. And we'll have to accept the fact that our replicas are going to temporarily diverge. And accepting this divergence is where we can get consistency errors, because some systems programmers have just decided to make this the programming model. Under a variety of weak consistency guarantees, if I perform a write at a single replica, and then I wait any amount of time, and I perform a read at some other replica, I might get a stale value. There's really no amount of time I can wait that'll be sufficient to guarantee that my write has actually propagated everywhere, even though the system swears it'll get there eventually. Surprisingly, this is hard to program against. Your programmers are basically having to deal with time travel, a phenomenon which inspires the name of some of the databases that offer this time travel behavior. And it leads to consistency errors. Okay, those are our 3 problems: handling data races, dealing with coordination overhead, and handling consistency errors. Now let's talk to solutions, starting with our consistency errors. And I want to start with an observation. There are some applications that are perfectly correct under weaker consistency models, or at least some parts of applications. So consider an online game service. We're going to want to do 3 things here. We're going to want to record wins and losses. We're going to want to perform some online matchmaking, and we're going to want to run tournaments where we invite like the 10 best players in the entire world to go compete for glory and blood, or whatever you guys do. I would claim that recording wins and losses is pretty much fine with weak consistency. If I win my 48th match of Smash in the course of a single hour on my Switch in a plane, I don't necessarily need the world to know that instantly, no matter how nice that would be. Other things, though, like running that tournament, they seem like they need stronger consistency. If I say I'm inviting the 10 best players in the world to compete for glory and blood, then there better be the 10 best players in the world, or else I'll get the blood part. It's into this domain that the Mixy language comes. Our goal is to write a new language for transactions in which the code that you write will run with as little consistency as possible, but still enough to satisfy your requirements. And it's papers we love, so this is a paper. I'll put a link later. Let's take a look at how we might implement that online game in this system. So databases, right? So I'm going to have 3 database tables. One tracking the wins, one tracking the losses, and one tracking the rank of a particular player, saying whether they're number 1 or number 2 in the entire world. I'm also going to write some transactions that manipulate the state of these tables. Like I might write a transaction that you call when a match concludes and a player wins and another player loses, and we record that. Or I might write a transaction that sends out invitations to the tournament, which grabs the 10 best players in the rank table and then returns me that so I can go email them. Now, all of the code that you're going to see in this presentation is like 98% completely as it would appear in my paper. I'm not leaving out some cumbersome annotations, or I'm not have 5,000 pieces of setup code that you're ignoring. This is really the code. And I also think, at least for myself, that it's kind of readable. So I'm going to sometimes give us time to read the code while I say things like, this code is really readable. in the hopes that you're fully ignoring me and just reading my slides. Don't actually do that. Right, so we've had time to look at this code now, and we need to figure out what consistency the code needs to run at. Well, I originally motivated that the recording of wins and losses doesn't need to have completely strong consistency. So let's run with that and put these annotations on our slides that say weak transaction and strong transaction. Mixy, the language and compiler, will recognize these and immediately determine that the wins and losses table can be associated with causally consistent or weakly consistent storage, but the rank table needs to be associated with strongly consistent storage. Okay, so far so good, but also so standard. If I just set an isolation level in a transaction in any language, it would do something like this. Where Mixy really shines is in its ability to recognize that consistency decisions are compositional. Consider this much larger fonted, I think. Actually, it's about the same length. Transaction for calculating the rank that goes into the rank table. What we're going to do here is we're going to first create a list that stores the win-loss ratio for our players. Then we're going to iterate through all of the players in the world, and we're going to divide their wins by their losses and shove it into the list. We're going to sort that list by the ratios so that it's actually in best to worst order. And then we're going to use the contents of that list to assign into the rank table a new refreshed ranking of all the people in the world. All right, quiz time. Who can spot bugs? I've been told there are at least two. Someone in the back can spot bugs. You're gonna have to shout super loud. There's something about the ordering of wins and losses not being guaranteed. I think that's coming up to the right answer, but I'm going to let someone else have a slightly more precise crack. Way in the front. That's true. Also, just before someone points it out to me, it's not necessarily guaranteed you've lost ever. But the larger transaction and bug here, the divide by zero you can fix. It just doesn't fit on the slide anymore. The larger bug here is that there's a consistency error. See, I said that the transactions that touch the rank are going to need to be strongly consistent. But I'm looking at weakly consistent storage in this transaction to do this calculation. How can I square that? If we were to just naively intersect the requirements of these transactions, we'd keep our wins and losses on weak storage, and we'd keep our rank table on our strong storage, and we'd get a bug. Because each of these transactions doesn't run at the abstraction of a database, it runs at a specific replica of the database. Our calculate rank transaction, therefore, is going to run at one specific replica. And it's not going to get the global view of what the rank should be. It'll get that replica's view. So when I then run the invite to tournament transaction with strong consistency against only strong storage, by then it's too late. I'm not going to get the top 10 players in the world. I'm going to get the top 10 players at a particular replica. And blood. Because angry players will send me emails, and I hate emails. I've already started learning faculty get way too many emails. This brings us to an important design principle for a language like this. Strong outputs must stay strong. Or more specifically, an observation that you know must be strongly consistent or linearizable shouldn't be influenced by observations that are weakly consistent. That's what our compiler is going to recognize. Track the code in your transactions and recognize that sort of improper influence at compile time, guaranteeing that you'd get an error when you try to run this calculate rank transaction, or rather when you try to specify it. And you won't just get angry emails or blood. Now, if I take a step back, what we're actually going to be able to do here is take advantage of not just two consistency levels, weak and strong, which have so far been referring to linearizability and eventual consistency, for those of you in the know. We're going to be able to build an entire lattice of consistency models, capturing isolation guarantees, memory consistency guarantees, that weird thing your Uncle Joe implemented yesterday in their system. And it all will fit. so that linearizability is the strongest thing that we enforce, and eventual consistency is the weakest. There's always a way to take two models and say, all right, what do these two have in common? Well, what's the least upper bound of these two models that guarantees at least that? Or what's the greatest lower bound, the one model that can enforce everything these two require? When we've got this sort of ordering, this lattice, we can specify what improper influence is formally. It just happens whenever a less consistent read, something that's up on this lattice, influences a more consistent write, something that's down on this lattice, or whenever two things that are incomparable influence each other. And even better, we can prevent this kind of improper influence via using an information flow type system, which is something from the security literature in which it is commonly used to prevent secrets from leaking out over public channels. Let's see how this works by looking back at our errant transaction. Note, we're not going to fix the divide by zero error. It's just going to stare at you in the face the whole talk. So the first thing we're going to do is we're going to use the storage as a source of truth. Previous examples, previous transactions that we've already analyzed have led us to believe that wins and losses are weakly consistent, while the rank is strongly consistent. We'll then be able to statically, at compile time, follow this flow, noting that the wins and losses will influence the win-loss ratios list, and the win-loss ratios list, in turn, will influence our rank table. And while all of this looks a little bit like direct flows, this technique is strong enough to handle everything, including like weird control flow branches where I'm using a inconsistent bit to decide which strongly consistent action to take. We capture all of that. The theorem is very strong. Using this information for this errant transaction, we're able to infer a contradiction. We're able to determine that, as the programmer has specified, these transactions cannot all exist in the same system. Now, this doesn't mean that you're not allowed to run tournaments, or that I'm actually secretly here to tell you that you just have to be slow and run everything linearizably, though that is quite a popular position to take, because you can fix it. In practice, if you've got a weakly consistent system, that doesn't mean you're doomed forever. A lot of them will expose operations like where you can specify manually that you want to read from an entire global quorum, every single replica, or you can just pause it for a minute and wait for that eventual to actually get up to be now, and then read after it's all converged. Mixy recognizes this too and allows you to expose primitives, like say a quorum read of a universal quorum, which will be automatically recognized at compile time as being equivalent to a dynamic upgrade. This isn't like we're going to ignore that this was weak and just pretend like it's strong. This is an actual runtime effect that leads us to believe the values are reliable now. With that kind of stuff, we're able to see the transactions completely strong and let you run exactly as you should have. Note, though, that we're doing this by telling the programmer that they were wrong, maybe giving them a hint that there were things they could have done, and then forcing them to do the quorum read. We're not trying to do like the database declarativity thing where we just magically create the correct code, and then you discover later it's magically 10 times slower because of some competing transaction. It's also worth noting that flows in the other direction, from strong to weak, are of course fine. It's all right to have extra consistency. No one will complain about that. So if I was to, for example, take my strong transaction invite to tournament and then actually send emails, Mixy would not flag that as an error, and emails are perhaps the least consistent thing that we could ever use. In summary, by preventing improper influence using an information flow type system, we can get reasonable semantics for our mixed consistency transactions. In particular, we can get that key guarantee that a strong observer will only witness a strong behavior. And while I'm talking to sort of a languagey audience, I want to emphasize that this is not just a language project. This is really implemented. We've written it as a shim over existing databases. It's 15,000 lines of C++, mostly templates. And the code is available right here, but also it's 15,000 lines of C++, mostly templates. So please treat me gently. Mixy solves part of our problem, but it does leave something of a question. How did I know what transactions should be weak and should be strong in the first place? How do I know that the programmers got the annotations right? I mean, all Mixy will tell me is the annotations are consistent, not that they're justified. Or to put it another way, is there a way for me to look at programs and say, I know that that part of the code will always be safe under weak consistency? And that'll bring us to our next batch of papers. That was really fast, sorry. I'm going to build out a system of reliable observations that will allow you to build correct code under weak consistency. So what do I mean by a reliable observation? This isn't some term of art from academia we forgot to tell you about. This is just a term I'm inventing now. It's just any observation that forms some guarantee about our distributed state. If I'm in a transaction and the transaction is strictly serializable and I read, then I've got a guarantee, a reliable observation that for the duration of my transaction, what I read actually reflects the state of the database, for example. But there are other classes of reliable observations that don't require such heavyweight mechanisms. Consider, for example, this predicate, that the wins of a particular player are at least 15. This is also a reliable observation, because we know how the system works, and we know that I'm never taking your wins away from you. Yeah, no, I really am not. I don't care if you're cheating. The reason this is reliable is because no concurrent mutations are able to modify it, are able to falsify it. Once your wins are at least 15, they're going to stay there. And that's true without transactions. That's true under arbitrarily weak consistency. It sort of forms a spectrum. More restricted mutations are always going to allow more general observations you can make. On one extreme of this spectrum, we're going to have things like constants, where they're constant. I can make arbitrarily deep observations about their state, and they're going to be reliable because there are no concurrent mutations. There are no mutations at all. We live in a beautiful functional land. On the other side, we have truly evil things like multi-writer registers or single-writer registers, which may change arbitrarily out from under us at any moment. So any observation we make can only be reliable with reliance on dynamic mechanisms. But there's some interesting stuff in the middle, things like counters that are only ever incremented or sets that are only ever added to. This is a class of objects that grow monotonically. They're inflationary. They always get bigger with respect to some natural order, like less than on numbers or like subset on sets. And they will support a class of reliable observations. In particular, they'll support a threshold observation. If I compare it with a constant and it's above that constant, that's stable. So in other words, if all of my shared objects only ever grow, and I'm only ever looking at thresholds or stable characteristics, then our program can be correct and even convergent, like under arbitrarily weak consistency. And you might have noticed that we've moved into the avoid coordination section. Added bonus, none of this relied on a dynamic coordination mechanism. So all of it can run at whatever speed your network's going to allow. None of it pauses, avoiding all the coordination overhead of something like Paxos. It's pretty cool stuff, but it's also not really new. I mean, there's at least 4 people I see in the audience who've done similar things. The real question that tends to come up, though, is, what can I do with it? I mean, I can compare constants for days, but what am I going to build? And it turns out you're going to build a lot of things. There are many core system components that are fundamentally monotonic. And to show this with style, we built out a full distributed system, Duratio. I'm not really here to talk about systems, despite the title. So I'll just do a really quick overview of how this works. Duratio is a state machine replication system. Basically, it gives you the abstraction of one computer being backed by multiple physical machines, so that if I shoot one of the physical machines, your abstract computer stays up. It's a well-trod problem space. It's perhaps like the default problem to solve in distributed systems, and it's been solved thousands of times before. But Duratio's fast. How fast? Like 10 times faster than Zookeeper, a competing solution in this space, fast. And we've written about it. We've got papers in a bunch of places. We did a tutorial at SOSP right before the pandemic. And we're building on it. There's new systems coming out that are a little stealthier than I knew when I wrote these slides, so I won't say any more about them. And all of this is powered at its core by monotonicity. Let me look at one particular monotonic protocol within Duratio, and so we can see exactly what I mean. And this is just going to be the simple stable message delivery protocol. In stable message delivery, I've got a message that's going to originate at one node, and I need to make sure that it's received at all nodes, but that each node only actually acts on the message if that message has arrived everywhere. So the way the protocol works is one node starts with a message, sends it to the friends. The friends all send acknowledgements both to each other and to the original sender. Once every single node has received all acknowledgements, as in if there are 3 nodes, they've received 3 acknowledgements, then that individual node knows that the message must be everywhere and so can actually act on it. Makes some sense? Hopefully. I saw some nods. I saw some people in phones. We're all good. Let's implement this using the primary monotonic data type of the Duratio system, the shared state table. In this table, rows correspond to individual replicas of the system, and columns correspond to basically variable names. Individual pieces of data will be interested in exploring. Individual cells contain things like counters or sets, any monotonic objects. They can be updated by basically inflating them. So you can run monotonic functions over it. You can do arbitrary compositions of those. You can do inflationary rights, and you can do threshold comparisons. Each of these individual cells is basically going to reflect the value of that column at that node. So the top left here, that green box, is the value of x at A. We've built out a custom domain-specific language that is going to guarantee that all the programs which use this shared state table must be monotonic constructively. It's a simple combinator-based language. And here's how we use it for stable message delivery. Well, message starts at A, so we're going to mark that the A node has received a message from itself. All right, sounds good. Message goes to B and C. B and C react to that by marking that the B and C nodes have received a message from A. In the background, everyone is running this continuous computation to check if the minimum of this column is at least 1. Minimum is a monotonic function, and 1 is a constant, and greater than is a comparison that goes in the right order. So this is all monotonic. Once that column is at least 1, we can conclude that everyone has received the first message from A, or rather everyone's received at least 1 message from A. And we can conclude stable message delivery. Victory, hooray. One major problem though, that table looked pretty damn centralized to me. And the whole point of this was not to be. So let's look at this again, except for now, our tables are weakly replicated and every node gets a copy of the whole table. So resetting state. Once again, we'll start with the message at machine A. So machine A will mark that it's received a message from itself, but now only machine A knows about it. The other tables haven't been notified yet. Machine A will send that message, and the other machines will get it and mark in their own respective tables. Now at this point, we're all still trying to figure out if we've been delivered, so we're just blocking on our minimum of column computation, but the machines are not well synchronized, so it's going to take a minute. In the background, all of these machines are communicating, exchanging the states in their various tables, merging them together. And eventually, we'll all be able to deduce that the minimum of the column is at least 1. And because that computation was monotonic, the fact that it has to wait for synchronization doesn't threaten correctness at all and doesn't require us to do any programmer reasoning. If you've heard of CRDTs, or if you've talked to the good people at Ink and Switch or the local first crew, same principle is at play. Using basic stuff just like this, we were able to build strongly consistent consensus, like the most strongly consistent protocol there is, entirely atop weakly consistent replicated tables. And because we used monotonicity, we didn't have to do any complicated proofs or complicated testing to make sure that individual races in replication weren't going to be a problem, because we got our convergence and our race freedom for free from the language. It's a perfect example of how better language design, more careful language design, can build better distributed systems. I'm just pausing because there's a lot of words up there and I don't want to say them. Now, of course, the next question I usually get after, is monotonicity useful? Can you build everything? Is sure, but not everything is monotonic. And you're right. Sometimes things are not monotonic. Sometimes things really are fundamentally subject to those data races. Remember the data race slide? And sometimes for those things, you'll need to use some kind of transaction or locking mechanism. But when I first introduced this, remember how I put a pin in something saying that it was an expensive thing to do at runtime? Let's go ahead and take that pin out now and return to the world of shared memory programming to talk about our last work, using type systems to avoid destructive data races. We are going to eliminate all destructive data races at compile time with minimal programmer annotation and either no or light opt-in runtime overhead. You'll use all your locks correctly. You'll never leave a dangling reference, or at least if you do, no one's ever going to use it. Another paper. So what such a system is going to have to do is enforce mutual exclusion. This is basically the principle that the parts of the memory that individual threads, like our gray and orange thread, are working on are independent, that they're never trying to do work on the same part of memory at the same time. And normally in a mutual exclusion system, you've got something like a dynamic locking mechanism, where I can acquire a lock to temporarily gain access to all of the memory the lock guards. This part turns out not to be very hard to model in types. The hard part is to deal with releasing the lock. Let's take a look inside the memory to see why. See, while our gray thread was holding this lock and was manipulating these objects, it might have formed references between the objects that it owns and the objects that the lock guards. And that's fine. It's holding a lock. The whole point of holding a lock is to manipulate the memory. But when we go to release the lock, we still need to guarantee mutual exclusion, which means we need to be sure that the gray thread will never use any of the references that go to the information it's releasing. Similarly, if another thread gets the lock, we need to make sure it can't follow pointers from the locked stuff into objects that the gray thread thinks of it as its own. Now, in order to do this, fundamentally, we need to figure out where those references are. And I have some slightly bad news. It turns out that tracking arbitrary references in a Turing-complete imperative language is undecidable in general. Literally computationally impossible. But honestly, that's not really that scary. I'm a programming languages researcher. We solve undecidable problems every day. And this particular undecidable problem has been solved before, a lot of times, most popularly by Rust. And Rust's solution is simple and elegant. Ban everything that's not a tree. Now, this works really well. Instead of tracking an unknown number of references into a locked region, we track one. And one is much more computationally feasible to keep track of. And it works, and it's super popular. There's probably a talk on it today. I didn't check. And I mean, industry uses it. We've written kernels in it. And there's only one slight problem. It turns out, work with me here, not all data structures are trees. Let's imagine for a moment I want to write a doubly linked list. So I would fire up my editor and start, and I'd get a compiler error, and I'd, Google it around and try to figure out what the good people in Rust, surely they write doubly linked lists. I wrote that when I was 12. Come on, Rust. And eventually I'm going to be sent, if I want to stay in safe Rust and I want to use the libraries and I don't want to learn about the stacked borrows paradigm, I'm going to be sent something like this. This is very bad. I mean, the font's a little small. I could have syntax highlighted it better for sure, but also the code is very bad. Each individual layer of types adds a little bit of runtime overhead, tracking a dynamic fact that you didn't need to know statically, or rather that you were sure wasn't going to be necessary to track. And even worse, sometimes these libraries are verified, so they're trustworthy, but they're not really in safe Rust. They're going to use unsafe internally. I can do better. One keyword, no runtime overhead, no reference counting under the covers, natural code. So how is that possible? Well, to understand that, we're going to have to understand why Rust loves trees so much. What's the problem that comes up when you have graphs? It's a challenge that I like to call path confusion. When two syntactically distinct paths through a data structure might or might not wind up getting you to the exact same place. Let's look at this in the context of our circular doubly linked list. Here I've got these blue circles representing the list spine, and these green boxes representing the payload stored at each position. I've also labeled all the pointers as a bonus treat for those of you really close to the front. The key thing a type system needs to do is check code, make sure that the clients that use this data structure are actually going to be able to avoid their races. So here's some code we might want to use. Well, we're going to take the first element of the list, put it in a stack variable head. We're going to take the next thing off of that head and put it in the stack variable second. We're going to send the head's payload to thread 1 and the second's payload to thread 2. And then the sender is going to exit. And again, if any of you are like, where's the borrow annotations? Like, this is real code. This is just what you'd write in my system. The thing my compiler will need to tell you is whether this code is correct, whether there can be any data races in this example. So, do we think there might be data races in this example? It's not rain, they're just applauding next door. Say a one-element list, perhaps? Indeed. There's nothing in the type signature that promises my list is any particular size. So while we might have a multi-element list, we also might have a one-element list. And we need to make sure that the code works in both cases. And it doesn't. In a one-element list case, the next pointer is just a self pointer. It'll point back to the same node. So when we send the payloads to two different threads, we're sending the same object twice. Our bug was that we wrongly assumed that the head and second payloads are distinct, which is really not allowed. So what our type system is going to need to do is be conservative. It's going to need to try to make sure that the program is correct with not just the abstraction of the data structure we have in our head, but with every possible representation that's allowed by the types we've written down. How are we going to do that? Well, basically what we're going to do is we're going to abstract our objects into sort of compile time determined collections that I call regions. Other people call this regions too. I didn't invent this one. And we're going to ask the programmer for a little help using this ISO keyword, which stands for isolated, to break the region boundary. Basically, anytime you follow a pointer that's not isolated, our type system will conservatively assume you might wind up back in the same place. So we'll just put a big orange blob for all of it. But every time you follow a pointer that is marked as isolated, we'll assume that you're in a completely new place, and in particular that you can't get back from that place to where you came from originally. Our isolated references now are actually going to form a static approximation of the graph that is a tree. So we get to, at this point, use all of the Rust tricks, but at the region level. Graphs within regions, trees across regions. There is a cost. Regions wind up being your unit of concurrency here. You can no longer statically split a doubly linked list and know that you've done so correctly, which, to be fair, is statically impossible, because if I gave you a buggy list, you'd just not know. Now there's an asterisk here, because if you're willing to accept a little bit of dynamic overhead, we can do this. Say, for example, if I wanted to have a dynamic check that made sure my list had at least two different elements, I could use this if distinct check, which checks to see if head and second point to different places, and if they do, in the true branch, will let you access their payloads independently, since we actually know that's safe at runtime. Or if you're feeling extra crazy, you can use an even stronger check to see if the head and second parts of the list are fully disconnected, if I've just split my list completely in half. In that case, I can treat the two halves of my list totally independently. I can send them to different threads. I can compute on them as I will. I don't have to worry about the thread that receives the first half of the list being able to mess with the thread that receives the second half. Now, using just these two dynamic checks and the large static system I alluded to, we built out a fully featured library, including all sorts of cool collection stuff that would have been previously impossible in Rust and other competing systems. It works, and it works so well we've actually proposed it for Swift. This is definitely a take a photo or ask for the slides later kind of link, but you can see on the Swift forums our particular proposal of a shade of this for the Swift system. And ultimately, that's pretty much what I wanted to talk to you about today. You can clap in 2 seconds. I'm so sorry. We've seen how to solve destructive data races, how to handle coordination overhead, and even how to deal with distributed memory consistency. So please go home, read a bunch of papers, and tell all of your industrial friends that we do cool stuff here and that they should come next time if there is one. Thanks, everyone.